Hi, okay, let's see if we can do this. Now you try example for adjunctions. So in the videos, we looked at binary code products, so disjoint unions or sums, as an adjunction to the diagonal functor, which takes an x and gives us back two copies of x, because it's in this category of pairs of objects from C to C. And now we are asked to do something similar, but instead of a left adjoint to this diagonal functor, we are looking at the right adjoint. So the first thing we have to do is we have to define it. And I have already given us what it should do on objects. So given a pair of an A and a B, we take their product, A times B. And then here, let's see what it does on mappings. So we're given a pair of morphisms F and G, because this is what morphisms in this pair category are. And we have to produce a function from A times B to A prime times B prime, if we see that F goes from A to A prime, etc. So we get given an A and a B. And now we have to make a pair of two things. Okay. And here in the first component, we see that the goal matches the output type of F. If we do F of something, and what's this something? Well, this matches the type of the A that we have. So we apply F in the first component, and similarly we can apply G in the second component. Okay, does this preserve identities? Well, this is an equation between functions, so we can use function extensionality. That means that we get given something. What is it? It's a pair of two things. So we get given A and a B. Now we need to show that the identity applied to this thing is the same thing, but that's obvious. So therefore fixes that. And what about composition? So again, this is the scary looking equation between functions, as you can see by the lambda here. So let's use extensionality. Okay, now we get given a pair of an A and a B again. And if I could type. Okay, and then here we see that again we just have to prove apple. That wasn't too bad. Okay, so we have defined the functor. Now we want to show that it's actually adjoint to the diagonal functor. So see what we need to do to that. We need to map in one direction, which is taking a pair of these morphisms, an F and a G. That's a morphism in this category, and then we have to make a morphism in set from X to the diagonal thing applied to the product. So let's see. So we got given an X like this, and we have to make a pair of two things. Okay, and then here we need something which is in the output type of F. So I think we can use F applied to X here. And here we need something which is in the output type of, sorry, I could get back to my the output type of G, so we can use G of X here. So that's one way. So we were given an F and a G, and then we made morphism in the other direction. So let's see if we can go the other way. So then we're given just some function H, and we have to make a morphism in the pair category. So that means that it's a pair of two morphisms. And here in the first component, we need to go from X to this thing. But that's what we get if we feed an X to H. When we have an X. So we're making a function, so we get an X given to us. And if we now give this to H, let's maybe do it step by step. Then we see that H is going to give us a pair of two things. So we can take the first projection here. And that gives us what we want. And similarly here, second thing, we got given an X. And if we give that x to h, then we get a pair of things, and this time we can take the second projection. Okay, so we managed to translate from and to these two different morphisms. And are these translations inverse to each other? Well, let's see. So here we get given an h. I have to show that going back and forth does nothing. Okay, if we want, I think ref will just work here. Yeah, we don't see that though. Then we could actually say this is an equality between functions. That's not quite true because h is already a pair of two things. So okay, since raffle works, let's just go with raffle. What about going the other way? Here we get given a k, and this time raffle is going to work again. Okay, and finally for naturality, we get an f and a g. Does this look the same? Okay, so the hard part, if there was a hard part, was just to define these functions to and from the morphisms, right? And then the proofs here were actually easy in this case.